such a thing like x to the power n, and if they want you to find the derivative of it, the answer is n times x to the power n minus 1. That's how you find the derivative of a function that looks like x to the power n. And that's what you have here, x cubed. Instead of n, you have 3. What does the rule say? Derivative of that is power comes to the front. There you go, and power minus 1. Okay, so 3 comes to the front, 3 minus 1, 2. Finished. Here, 2 comes to the front, and there is already 24 there. So 24 times 2 is 48. And 2 minus 1 is 1, so we don't even bother writing it. Plus 45, keep the 45. Derivative of x, don't calculate, memorize. From the previous sessions, it's 1, so we don't bother writing it. And derivative of a number, like minus 12 is 0, so again, we don't bother writing it. Okay, so you found the derivative. Now find what makes it 0. Find what makes this derivative 0. Well, it's very easy because you're going to use your calculator. And multiply 3, because this is a quadratic expression, like 3x squared plus 48x plus 45. You're just going to type to your calculator your a, which is 3, your b, which is 48, and your c, which is 45. Or, before doing that, as if it is very difficult for the calculator, I just simplified it a bit. I wrote this equation instead of this one. It is the same thing. It's just simplified version of it. I divided the entire equation with 3. So if you divide 3 with 3, it's 1. If you divide 48 with 3, it's 16. And if you divide 45 with 3, it's 15. So they're identical equations. In my calculator, I wrote a equals 1, b equals 16, c equals 15. But who cares? You can also write 3, 48, and 45 to your calculator. And the calculator is going to give you, well, maybe no result, maybe only one result. But in this case, it gives you 2 results, minus 1 and minus 15. Now, this is the first and probably the most difficult thing you do in these questions. You are almost finished. Then what you are going to do is you are going to locate these numbers on x-axis. Well, there is your axis. Well, I didn't want to draw a straight line. I put it with dashes. So, well, I don't know, maybe 0 is here, and there is your minus 1, and there is your minus 15. Okay? Now, but the real point is this. Now, when you put these numbers on the x-axis, minus 15 and minus 1, eventually, they divide the axis into 3 parts. This is the first part, where this is the second part, and where this is the third part. Okay? Now, what you're going to do is this. From the first part, you pick up a number, any number you want, here. Okay? Any number you want. Now, pick up a random number from the left-hand side of minus 15. Okay? For instance, pick up, well, why not? Minus 16. Of course, you can pick up, if you want, minus million or minus 10,000, whatever, but it's just going to make your life more difficult. So try to pick up a reasonable number. I'm going to pick up a number which is smaller than, or on the left-hand side of minus 15, and I picked up minus 16. I didn't go too far. So find the value of the derivative at that point. So you are going to write minus 16 in the derivative. That's the expression of the derivative. So you see, I'm writing minus 16 in the derivative. So it is 3 times minus 16 squared, yep, plus 48 times minus 16 plus 45. And your calculator is going to give you the result of 45. Okay, now this is the important part. This 45 is a number greater than 0. So our rule in this subject says, if the derivative is greater than 0, which is the case with us, then there the function is increasing. Okay, where did you pick up this number from? Minus 16. You picked it up from here, isn't it? From the first part. Okay, so you're going to say this. So from minus infinity up to minus 15, this function is increasing because the derivative there is positive. And I say from minus infinity because the beginning of this line is at minus infinity. Okay? Now I will do exactly the same thing 2 more times, here and here. Let's do it. Now I'm going to pick up a random number from this interval, a number that is greater than minus 15, and a number that is smaller than minus 1. Well, I pick up minus 2. As I told you, you can pick up if you want minus 14, but it's just going to make your calculations more difficult, maybe. So I picked up minus 2. It's a small number, and it is in this interval. So I just take it and write it in the derivative. Okay? That is the derivative. So I write minus 2 there, the number that I picked up, in the derivative. 3 minus 2 squared plus 48 times minus 2 plus 45 equals, if you make the calculation, it is minus 63. Now, this is a number smaller than 0. So the same rule now says if the derivative is smaller than 0, then there the function is decreasing. Okay? But where? From where did I pick up this number? From this interval. Okay, so what I say is this. From minus 15 up to 1, up to minus 1, sorry, this function is decreasing. Now I will do exactly the same thing for a third time and the last time in our third interval, which is numbers greater than 1, minus 1. Now pick up a random number from the right-hand side of minus 1. For instance, pick up 0. Yeah, why not? Because 0 is there. And it's a very easy number to make calculations with. So I pick up 0. Find the value of the derivative now at 0. Just write 0 in the expression of the derivative. What is going to be the answer? If you use your calculator, it's 45. It's a number greater than 0, isn't it? Yes. So the same rule says, as it has already said in the first part of the question, the function should be increasing there because the derivative is greater than 0. Okay? So from minus 1 up to infinity, because there is no end of this line, this function is increasing. So overall, our answer to this question, find where this function is increasing or decreasing, well, it is increasing till the point minus 15. Then starts decreasing till the point minus 1. And then it starts increasing again forever. So probably it looks like this. I don't know the graph of this function, but it should look like this. There is my minus 15, and there's my minus 1. Okay, so up to minus 15, this function is increasing. After minus 15 till minus 1, it is decreasing, and then increasing again forever. That's the conclusion I had about the behavior of this function by using the derivative. That's it. Okay, take the derivative, create your intervals, pick up numbers, and make your test. B part of the question. As I told you, each of these questions will have 4 parts. The B part says, find the critical points of fx, if any, and classify them. Now, what does a critical point mean? A critical point is a point where the derivative is 0 or the derivative doesn't exist. Now, in our cases, in this course, we won't have this case where the derivative doesn't exist, is not going to exist in our questions. In our questions, critical points are going to be the points where the derivative is 0, which we have already found. We found the derivative, we made it 0, and we found the numbers, what makes this derivative 0, minus 1 and minus 15. Okay, there you go. In our case, when the derivative is 0, x is either minus 15 or minus 1. These are our critical points. Okay. Also remember the answer of the part A, the function was increasing till minus 15. Then it started decreasing till minus 1, and then it started increasing again forever. This I copy-pasted from the answer of the first part, A. Now, what I'm going to do is this. I'm trying to understand what is this minus 15 and what is this minus 1. Now you will see what do I mean by asking what is this. Now, classification of the critical points. From above chart, we see that. Pay attention. Up to 15, the function is increasing. After 15, minus 15, function is decreasing. So 15, minus 15, should be a local maximum. What does it mean? It means this, because here is your point, minus 15, and up to this point, the function is increasing, and after that point, it starts decreasing. Well, doesn't it look like a maximum? As you can see, the function doesn't take any higher value. That's why we call it a maximum. That's how you classify the critical points. Let's do the same thing for minus 1. Up to minus 1, the function is decreasing, and after minus 1, the function is increasing. Well, sure, so it should look like this. I don't know this function, but there is minus 1. Up to minus 1, this function is decreasing. After minus 1, it starts increasing. Doesn't this point look like a minimum point? The function doesn't take any lower value than that. Okay, so we call minus 1 as a minimum point. That's it. That's how you make the classifications. This is minus 1, not minus 15, sorry. Minus 1 is a local minimum. Okay? That's it. So there is also the C and the D part of these questions. Let's go on. C part of the question. Find the intervals where fx is concave up and down. Now, let me first explain that. What does it mean here? What does it mean concave up? Well, concave up means the function's graph is going to look upwards. Okay? Anything that is a part of this curve that looks like this curve is called concave up. Or anything that looks like this is called concave down. Okay, because it is looking downwards. Okay. So for example, when you look at this graph, this fx, whatever it is, well, here I see a function that looks upwards. Okay, it's concave up. But from here on, it starts looking downwards, isn't it? Like concave down. And then, I don't know, around here, maybe, around here, it again started looking upwards. Okay. And maybe here looking a bit downwards, and etc. You see, concave up, concave down, and then up again, and then down again. Now they're asking us to identify, to find the intervals where it is concave up and down. How do you find it? Well, in order to solve this question, you need not the first, but the second derivative of the function. What is the second derivative? For a start, we show it like this. F double prime x, not 1 prime, but double prime. Well, it is, of course, very simple, something very simple. It is a derivative of the derivative. First, you find the derivative of the function, and then you find the derivative of the function. It happens to be the second derivative of the function. Okay, let me do that. Let me first find the first derivative of the function, and then take another derivative of that function. But I have already found this at part A, because I needed it. There it is. That's the first derivative of the function. So copy, paste. Now I will take the derivative of this, again using the same rules. The second rule, what says derivative of this is this. Okay, power comes to the front, power minus 1. Okay, there you go. That's your power, 2. Power comes to the front, 2 times, and there is already a 3 there, so 3 times 2 is 6. Power minus 1, 2 minus 1 is 1. So we don't bother writing it. Plus 48, 48. Derivative of x, don't calculate, memorize. It's 1. So I don't bother writing it. And derivative of a number is 0 from rule 1. And I don't bother writing it. Now I will find what makes this 0, as I did the same thing in the A part of this question. Okay? What you do is always the same. Take the derivative and make it equal to 0. Okay? Or in this case, take the second derivative and make it equal to 0. Now, 6x plus 48 equals 0 means if you take this plus 48 to the other side as minus 48 and divide both sides with 6, your x is going to be minus 8. Okay? So locate this number on x-axis as I did in the A part of this question. Just write minus 8 on the x-axis. Now, of course, this minus 8 divides x-axis into two parts. The first part here and the second part here. Again, I will do exactly the same things what I have done at the A part of this question. I will pick up a random number from left-hand side of minus 8, and let's immediately do that. Now pick up a random number from the left-hand side of minus 8, for instance, pick up minus 9. As I told you, if you want, you can pick up minus 1,500, that's up to you. But I pick up minus 9 because it's a modest, reasonable number, what makes my calculations easier. So I picked up that. Now, what am I going to do with that number? Write it in the expression of the second derivative. 6 times minus 9 plus 48. Find the answer. It is minus 6. Now comes our new rule. The rule in this part says if the second derivative is smaller than 0, which is the case with us, the second derivative of the function is smaller than 0, then the function is concave down. So it should look like a part of such a curve. Okay, it should be looking downwards. Okay, where does this interval start? At minus infinity. There is no end of it on the left hand side. So from minus infinity up to minus 8, this function is concave down. That's our conclusion. Now I will do exactly the same things now at the second interval. I will pick up a random number from there, and I will write that number in the second derivative. Which number would you pick up from this interval? Minus 7? Minus 5? I would pick up 0, because it's a very easy number to make calculations with. Now pick up a random number from the right-hand side of minus 8. For instance, pick up 0. Okay. Find the value of the second derivative at that point. Well, write 0 in the expression of the second derivative, and there you go. 6 times 0 plus 48 equals 48. Now it's a different answer, because now it's greater than 0. The answer is greater than 0. The same rule says now, if the second derivative is greater than 0, then the function is concave up, which means it should look like this. Okay? So from minus 8 till infinity, because there is no end of this interval, this function is concave up. So our overall summary is this. Up to minus 8, it's concave down, and after minus 8, it's concave up. Around here, it looks like this. Around here, it looks like this. And D, and the final part of this question. Okay? Find the inflection point, if any. What does it mean, the inflection point? Well, inflection point candidates, I call it like that, are the points where the second derivative is 0 or undefined. But again, you can guess that this is not in our subject. We focus on these ones, where the second derivative is 0. So let me find the second derivative, and let me find what makes it 0. But I have already found those things. This is the second derivative, and I found what makes it 0. It is minus 8. So that's my candidate for inflection point. And also remember that before minus 8, the function was concave down, and after minus 8, it was concave up. It's the result of the part C of this question. Okay, it's just a copy-paste. Now, what I'm going to say is this. From the above chart, we see that up to minus 8, the function is concave down. After minus 8, it is concave up. So minus 8 is an inflection point. Yes, when the concavity changes around a point, we call that point inflection point. Okay, so the function looks like this. Up to minus 8, it's concave down. You see, it's looking downwards. But suddenly, after minus 8, it starts looking upwards. Okay? So therefore, such a point is called an inflection point. So find the inflection points. I found that's -8. I had only one candidate for a inflection point, a number that makes the second derivative 0. It's -8. And I checked if the concavity changes around it. Yes, it changes. Before -8 is concave, then after -8 is concave up. So this point, -8, is an inflection point. That's it. That's our subject. I will solve one more question. Okay? Again, it will be exactly the same type of question. It will have 4 parts, A, B, C, D, and we will do exactly the same things. But now the function is different. It is now, of course, the function is different, otherwise the question would be identical. Now they give us this function, okay? And the A part of the question is identical with the A part of the previous question. Find the intervals where this function is increasing and decreasing. What our recipe says us, the instructions, or if you want to hear it like that, take the derivative of this function. Okay, let me take the derivative of the function by remembering that the rule 2 from last session. Derivative of such an expression is this. Okay, so 4 comes to the front, power comes to the front, power -1. 4 comes to the front, power -1. 4 minus 1 is 3. Now 4 times 0.25 is 1, and there is a minus here, so the answer is -1 x to the power 3, and I don't bother writing 1. You can use your calculator, of course. Here, power comes to the front. There is already 3 there, so 3 times 3 is 9. And power -1, 3 minus 1 is 2, and we are done. And plus, there is 200, but it's a number at the end. Derivative of a number is 0. I'm done. I'm finished. That's it. That's the derivative. Now, I'm going to find what makes this derivative 0. There you go. Now, you look at this expression and you may say, but I don't know how to solve this. I can't use mod 5.3 because it's not a quadratic expression. It has a cube in it. And you are right, you can't use mod 5.3 here, but you can make a tiny trick, and you should be able to understand this trick. Now, I will try to explain it to you. What I'm trying to solve is this. -x cubed plus 9x squared equals 0. Okay? What is this number, -x cubed? Well, it means x cubed multiply x with itself 3 times. Is it not? Yes. Plus 9. What does this x square means? Well, it is multiply x with itself 2 times. And those are the only things what I have in this left-hand side of this equation. I have 2 terms. This one, which is this, if you write it open, and this one, the second term, which is this. Okay, so I wrote the same thing, nothing new. But why I do this? Because I'm trying to observe what is common in these things. Well, there are 2 x's common in both of them, which I can take out. Okay, so if you take those common x's out, you are going to left with what? A minus and the leftover x here, plus the 9 and nothing else. Because I took both of these x's out. So these are identical expressions. Instead of writing this, you can write this, you see? -x plus 9, and you're going to say, is this x squared? Yes, because x times x is x squared. Okay? But does it really help me to solve this equation? Yes, it helps. Because now what I see here is this. I have multiplication of 2 things, isn't it? I multiply x squared with -x plus 9. I have multiplication of 2 things, and the answer is 0. Look, if you multiply 2 things and the answer is 0, if the answer is 0, one of them should be 0. Either x squared should be 0, which means x is 0, or -x plus 9 is 0, which means x is 9. Okay, so I found what makes my derivative 0. It's either 0 or 9. Okay, so the rest is the same story. I locate these two numbers, 0 and 9, on the x-axis. Okay, so eventually they divide x-axis into 3 parts. This is the first part, this is the second part, and this is the third part. From the first part, from the left-hand side of 0, I will pick up a random number, and I pick up -1 because it is a simple, modest number, and I'm going to plug it in the derivative expression, which is this, or this, for that matter. Minus x cubed plus 9x squared. There it is. I wrote -1, the number I picked up in the derivative, and the answer is 10. It is greater than 0. So my rule in this subject at this part of the question says, if the derivative is greater than 0, then there the function is increasing. Okay? So from -infinity up to 0, this function is increasing, because this line starts at -infinity. No? There is no end of it at this side. And up to 0, this function is increasing, because the derivative there is greater than 0. I will do exactly the same things 2 more times at the second interval and the third interval. Now, from the second interval, let's pick up a random number. Let's pick up, say, 1. Why not? It is there, and it's a simple number to make calculations with. So I pick up 1. Let me do the same things. Just write 1 in the first derivative. And if you write it there, instead of x, -1 cubed plus 9 times 1 squared is 8. If you make the calculation with your calculator, it's 8. So, which means the derivative is greater than 0. Well, the rule, of course, says the same thing then, because it didn't change. If the derivative is greater than 0, then there the function is increasing. Okay, good. So where I was, in this interval, from 0 to 9. So from 0 to 9, this function continues increasing, because it was already increasing. Okay, I note it down. And the third and the final interval, I will do the same things. I will pick up a random number, say 10 now, and I will write that number in the derivative expression, which is this, minus 10 cubed plus 9, 10 squared. Okay, so if you make the calculation with your calculator, of course, the answer is -100. Okay, -100. It's a negative number. A negative number. So now the rule says if your derivative is smaller than 0, then the function is decreasing. Okay, yes, my derivative is smaller than 0, so the function there is decreasing. But what is the interval? It is from 9 up to infinity. There is no end of the line there. So from 9 up to infinity, this function is decreasing. So the overall answer is this. From -infinity up to 0, it's an increasing function. Okay. From 0 to 9, it goes on increasing. Good as well. After 9, it starts decreasing. That's our summary. That's our answer. Okay. B part of the question is identical to the B part of the first question. Find the critical points of fx, if any, and classify them. So what is a critical point? A point where the first derivative is 0, or the first derivative doesn't exist. But I told you that this case is out of our syllabus. So we focus on only this case, where the derivative is 0. So first you have to find the derivative and find what makes it 0, which we already did. There's the first derivative, and we have found what makes it 0. It's either 0 or 9. Okay? 0 and 9. These are our critical points. And also remember from the first part, end of the first part, from this line, simply, from this line, copy-paste. Function is increasing up to 0, and up to 9. It goes on increasing, but after 9, it starts decreasing. Okay, so let's make an examination of these points. Let's start with 0. Now, up to 0, your function is increasing. After 0, it goes on increasing. So 0 is neither a local maximum not a local minimum. But it's, I think, obvious, isn't it? This is 0. There is your function. Let it be black. It's increasing up to that point. Okay, fine. But then it goes on increasing. So obviously this point is neither a maximum nor a minimum. It's not a maximum because the function takes higher values afterwards. And it's not a minimum because the function takes lower values before. So it's nothing. And it's our answer. It's nothing. But 9 is not like that. Because up to 9, the function is increasing, and after 9, it's decreasing. So 9 should be a local maximum. Why? Because if this is 9, the function increases up to that point, increasing, but after that point, it starts decreasing, which makes this value a maximum value. It doesn't take any higher value than that. So we call it a local maximum. C part of the question is again identical to the C part of the first question we have solved. Find the intervals where fx is concave up, concave down, where the graph of the function looks upwards or where it looks downwards. Okay, how to find it? Well, now you have to find the second derivative of the function. The second derivative is the derivative of the first derivative, which we have found in the A part of this question. There it is. There is the first derivative. Copy, paste. Okay, and then you're going to find the derivative of this thing, which is going to be your second derivative. Well, again, the same rule, of course. Power comes to the front, power minus 1. Second rule for derivatives. Okay, so power is 3. It comes to the front. There is your 3. And power minus 1, 3 minus 1 is 2. So it's minus 3 times x squared now. Plus, power is 2. 2 comes to the front. And there's already a 9 there. So 9 times 2 is 18. And power minus 1, 2 minus 1 is 1. So I don't bother writing it. So it's x. Now I'm going to find what makes this 0. Okay? That's it. Now you can use your calculator, by the way, easily. You can use mod 5.3. And your A is the coefficient of x squared is minus 3. B, the coefficient of x, let me write a proper B. What is that? Okay. Your B, coefficient of x is 18. And C, the constant number is, but there is no constant there, it's 0. Okay? So if you type these values in your calculator and use mod 5.3, okay, you are going to find these two answers, 0 and 6. The rest is the same story. We are going to plug these numbers, or rather locate these numbers, on the x-axis, and there you go. And once you locate them, of course, they eventually are going to divide the x-axis into 3 parts. The first part, the second part, and the third part. Okay? And you know the rest of the story. Now we are going to pick up a random number from the first part, a number that is on the left-hand side of 0. Well, I pick up minus 1. Because again, that's a simple, modest number. And then find the value of the second derivative at that point. Just write minus 1 in the expression of the second derivative. Minus 3 times minus 1 squared plus 18 times minus 1, and find the value with your calculator. The answer is minus 21, smaller than 0. Okay, so the rule says here, if the second derivative is smaller than 0, then there the function is concave down. So from minus infinity up to 0, because it starts at minus infinity, okay, that's the end of the line. But up to 0, this function is concave down. Now do the same things 2 more times for the following 2 intervals. Of course, let's go on with this interval, the second interval. Now you have the 0 to 6. Okay, pick up a number from there. Well, I pick up what? 1. Because that's an easy number. Now write 1 in the second derivative. So it's going to be minus 3 times 1 squared plus 18 times 1. And if you make the calculation, the answer is going to be 15, which is greater than 0. So the rule now says if the second derivative is greater than 0, then there the function is concave up. Okay, that's another conclusion of ours. So from 0 up to 6, this function is concave up. Okay, and the final interval, the third interval. Pick up a number from the third interval, and I picked up, no, not 7, I picked up 10. Because it makes the calculations easier. Well, because I don't use calculator. Okay, you can use calculator and you can pick up 7. And if you use calculator, you can also pick up 1 million. It's up to you. I picked up 10 because it makes my calculation easier. If I write 10 in the expression of the second derivative, I will find minus 3 times 10 squared. There you go. Plus 18 times 10. Well, now I can make this calculation from my mind, I mean. 10 squared is 100, so 3 times 100 is 300, but there's a minus, it's minus 300. And this is 180, so if you add them up, it's minus 120. You can use your calculator, no worries. It's a number smaller than 0, so the same rule says if the second derivative is smaller than 0, the function there should be concave down. Okay, so from 6 up until infinity, this function is concave down. Now, my overall summary of these conclusions, sorry, not consequences, but conclusions are: up to 0, the function is concave down. Between 0 and 6, it's concave up. And after 6, it's concave down. And we are finished. And the very final thing, what I will do today is the D part of this question, which is identical to the D part of the first question. Find the inflection points, if any. Now, this doesn't need to be plural. Find the inflection points, if any. So the inflection point candidates are the points where the second derivative is 0 or where the second derivative is undefined, which is out of our scope in this course. We are just going to find the second derivative and the points, what makes it 0, which we have already found. There it is. That's the second derivative. And 0 and 6 are the points, what makes the second derivative 0. We found it with mod 5, 3, and etc. Okay, so these are our candidates for inflection point. Also, from the answer of the first previous part, which is this, just copy paste. There it is. We remember this. Up to 0 is concave down, between 0 and 6 is concave up, and after 6 is again concave down. So now, let's check. Slow down. Up to 0, the function is concave down. After 0, it is concave up. So 0 is an inflection point because the function gets inflected there. There is 0. Up to 0, it is concave down, so it's looking downwards. Okay. And after 0, it is concave up. It starts looking upwards, the function. So we call that point as inflection point. Good. That's one conclusion. And we have one more candidate, which is 6. Let's see what goes on with 6. Up to 6, the function is concave up. After 6, the function is concave down. So the concavity behavior has changed, which means x equals 6 is also an inflection point. And let me try to give you an idea on a graph. Well, up to 6, this function is concave up. I don't know, maybe it looks like this. Like this, maybe. Okay. But after 6, it is concave down. You see? Up to 6, it was looking upwards, but after 6, it started looking downwards. Okay. So this point is an inflection point. Finished. I have one more question, which is exactly the same. Okay? But I'm not sure if I should squeeze it to this week. I think it's enough for now. I will leave this question to the next week because we actually have 2 weeks for these subjects. Okay, so the third and the final question, third and the final question, I keep it for the next week. Okay, and we are going to see each other again on, I suppose, on what, Friday? No, sorry, Thursday, maybe. I don't remember. In the second session, in the second session in this week, we are going to make a review for the assessment, okay, or the quiz, second quiz, what you are going to have at the Thursday evening, again between 6 p.m. and midnight. It's going to be the same type of thing. It's going to be, that will be 10 questions, multiple choice. You will have 1 hour, but you will have in total 6 hours to get online and do the quiz. And it is going to be entirely about derivatives. So we are going to make a revision of derivatives in our second session in this week. I don't remember the day, I'm sorry. It should be on what, Thursday, I think? Thursday or Wednesday, sorry, I don't remember. But yeah, whatever. On that day, we are going to make a, let me check it. What are you? 175 into Wednesday, okay. On Wednesday, we are going to make a revision, yes, of this subject, derivatives. Otherwise, if you have any questions, I will be here for 15 more minutes. I can repeat anything you want. There's nothing difficult in this subject. It's just a recipe. Just follow the recipe and you will solve every question. On Wednesday, Sakar, yes. On Wednesday. Otherwise, thank you for your attendance and see you on Wednesday for a revision for the second quiz that will take place on Thursday. Thank you, Sakar.